The ancient world was a fascinating place in many ways. Like the modern world, it was apparently full of technological wonders born from the observations of the natural world and the scientific thought and experiments that those observations most certainly inspired. On this channel, I've often discussed legends and accounts of acoustic levitation in both ancient times as well as in more modern times, as with the work of John World Keeley. But interestingly, legends of magnetic levitation were also common during ancient and medieval times, usually taking the form of floating statues of iron. Could magnetic temples have really been created to levitate life-size statues of the gods and other large monoliths? Was magnetism harnessed as an unseen mystical force to create gravity-defying miracles, pseudo-miracles, which would instill awe and devotion in the hearts and minds of the temple adherents? You won't want to miss this fascinating discussion of science and magic. In some cases, it appears that the ancients saw magnets as objects with almost magical properties, having the ability to reach out and exert invisible forces over a distance. To thinkers and philosophers of the times, magnetism resulted from vitalized emanations, which were ultimately divine in origin, and which permeated all matter. This theory translated well into 17th and 18th century mysticism, philosophy, and ether theories, which suggested that a type of radiation or fluid emanated from and permeated all things, especially from the stars, human beings, and magnets themselves. The writings of 16th century Swiss physician and philosopher Paracelsus abound with instances of this theory. He asserted that every substance in itself contains something of the nature of the lodestone, that an astral light, one of the finer media of nature, finer than the luminiferous ether, existed throughout planetary space and especially around the human brain and spinal cord. He wrote that humans are simply organized magnets, each with poles that attract and repel, and that our thoughts are magnetic emanations projected from our minds. We might notice that these thoughts are very similar to the theories of Edward Leete Skowron, builder of the famed modern-day megalith Coral Castle, who believed that streams of microscopic magnets composed all physical objects and were also the true source of all energetic phenomena. Similarly, German physician Franz Anton Mesmer stated that in the human body particularly are observed properties analogous to those of the magnet, a property that he termed animal magnetism. He says, It is shown by experiment that a matter flows out so fine that it penetrates all bodies without apparently losing any of its activity, its virtues being which may be accumulated, concentrated, and transported. In addition, the article states that analogies with magnetism were inevitable because of the properties of the magnet were known to ancient peoples. Some authorities claiming that it was used in religious rites in Egypt, Greece, and Rome. They offered as evidence the iron rings and wings used in the Samothracian mysteries, the iron wings worn by priests of Jupiter to increase their magic power, and the various symbols ascribed to the paganistic gods. It was said too that meteor stones, because of the force that they radiate, were used in religious rites, either as objects of worship or as tools for divination and soothsaying. For magnets to be available as an apparent source of mystical-like power, possessing the curious ability to exert telekinetic-like forces, it was only a matter of time before magnetism was employed in more visual and spectacular ways. Several accounts relate that one of these ways was in the levitation of life-size iron statues. The source of one such ancient account was a person known as Pliny the Elder, who lived in the 1st century AD. The temple of Arsinoe was to be vaulted with magnetic stone, or lodestone, in order to receive a hovering statue of iron. The temple and magnetic arrangement were to be commissioned by Ptolemaeus Philadelphus and his architect, who both apparently died before the project could be completed. Another claimant was Cedrenus, an 11th century Byzantine Greek historian, who related that an image in the Serapeum at Alexandria was suspended by magnetic force. And Cassiodorus, 6th century Roman statesman and renowned scholar of antiquity, stated that in the temple of Diana hung an iron cupid without being held by any band. In certain eras of antiquity, the common peoples likely would not have been fully aware of the scientific principles of magnetism and electricity, although this is unlikely to have been the case with the more educated classes, such as the nobility, skilled workers, and especially the priesthood. And hence a magnetically floating statue would have seemed miraculous indeed, and to the people would have confirmed the presence of the gods. These false miracles, as we would call them today, would have continuously renewed their religious and financial devotions. But would such a technique of large-scale levitation have really been possible, especially in ancient and medieval times? Or are these merely legends? Well, as previously mentioned on this channel, legends often contain kernels of truth. However, it may be obvious to some versed in the principles of magnetism that there's a glaring issue with these accounts. In the mid-1800s, mathematician and physicist Samuel Earnshaw proved that stable levitation is impossible with any combination of or configuration of electrostatic charges. The theorem applies equally to any combination of permanent magnets, paramagnets, metals, and static electromagnets. Stable levitational equilibrium requires points of local maximum and minimum values, which these combinations alone lack. Methods to work around this theorem include time-varying or position-varying devices such as pulsed electromagnets and diamagnets, respectively. Permanent magnets and ferromagnetic materials, which can become permanently magnetized, refer to fixed, innate magnetic fields. But paramagnets and diamagnets have magnetic fields which only emerge when in the presence of an external magnetic field. In the case of paramagnetic materials, an external magnetic field induces inner fields in the same direction as the applied field, causing them to be weakly attracted to it. In contrast, diamagnetic materials exposed to external magnetic fields respond with induced fields which oppose the field. It is essentially an atomic variation of Lenz's law, which states that induced magnetic fields oppose the chains that form them, resulting in repulsion of any applied external magnetic field. This repulsive diamagnetic field can also adapt to changes in the external field and is always repulsive regardless of the polarity. Undoubtedly, the ancients would have realized this apparent prohibition of levitation solely using magnets and metals, though of course they would not have called it Earnshaw's theorem. But if they were successful in creating a stabilized magnetic levitation system, then how would it have been achieved? Well, one way that we achieve it today is using the aforementioned diamagnets. The strongest known diamagnet, of course, is the superconductor, but this is on the extreme end of the diamagnetic spectrum. Weaker natural diamagnets used in lower-tech levitation include materials such as bismuth and graphene. Diamagnetism is generally millions of times weaker than the forces between magnets and ferromagnetic materials. But arranged in conjunction with strong magnets, they can enable stable levitation. In perhaps the most common diamagnetic configuration shown in the figure here, a magnet is positioned just below a larger lifting magnet. The magnetic force between the two magnets begins to lift the smaller one. However, this lift is unstable, and the magnet will either just move around and not be lifted, or will be instantaneously pulled up into direct contact with the larger one. But by placing diamagnetic plates above and below the smaller magnet, a stabilized vertical position of minimal energy can be reached, as the diamagnetic elements exert just enough repulsive counterforce if the magnet were to move too close to or too far away from the lifting magnet. Note also that in this position there is inherent horizontal stability, as tends to be in most setups involving attractive levitation. Arrangements involving repulsive levitation, on the other hand, tend to have inherent horizontal instability. Even on a small scale, this is quite fascinating and almost magical. We can imagine the feeling if this could be accomplished on a much larger scale. And so this brings up the question, were the ancient builders able to accomplish this on a large scale hundreds of years ago? Well, interestingly, the following article claims this very thing. It describes the construction of the Sun Temple, also called Serial Dul, a 13th century temple in Konark, in Odisha state, India. It was dedicated to the Hindu sun god Surya. The temple has been said to have contained a magnetically levitated iron statue of the sun deity. The particular setup involved a giant 52-ton lodestone magnet embedded within the ceiling, as well as a unique arrangement of magnets and metals concealed within the temple walls. Reportedly, between any two stone pieces lies an iron plate. The temple itself was constructed from oxidized and weathered ferruginous sandstone, or sandstone which possessed iron oxides. It also says that the Sun Temple took 12 years to build and involved 12,000 workers, carefully positioning iron and magnets in between layers of stone. Now, the mainstream narrative says that the temple is attributed to King Narasimhadeva, the first of the Eastern Ganga dynasty, with its construction being overseen by Shiva Samantaraya Mahapatra. But the account given here adds another figure of the story, named Bishu Maharana, as Mahapatra's chief architect. Bishu was apparently an expert in ferromagnetism and had studied ancient Egyptian architecture in great detail. However, he was having great difficulty in achieving any degree of stable levitation of the iron statue, as anyone who has attempted to do so would expect. The article goes on to say that Bishu's son, Dharmapada, is the one who came up with the solution, having played extensively with his father's vast magnet collection. He apparently had attempted magnetic levitation on a small scale, something that his father seems to have neglected. During his experiments with graphite blocks, Dharmapada had become aware of this property of diamagnetism and how to use it for levitation. The article says that a magnet must not be too close to either the top or the base. He knew the exact calculation. More than this was the choice of diamagnetic material, which was to be pyrolytic, graphite, or bismuth. He had practiced many times to surprise his friends, offering his expertise to his father by sandwiching the graphite blocks with cupula or bismuth, and by adjusting their position, the magnetic sun god was suspended and perfectly balanced in midair. The statue is also said to have had a large diamond attached to its headgear, such that the first rays of the morning sun would strike the diamond and light up the entire inner sanctum via reflection and refraction. An illuminated levitating statue would have been miraculous indeed. But would lodestone have been strong enough to do what is claimed? Natural lodestone is significantly weaker than today's permanent magnets. The holding strength of a magnet depends on both its field strength as well as its size or surface area. Field strength is defined as the amount of magnetizing force. It will be strongest at the poles and grows weaker the farther from the magnet. And so the stronger the field strength, the farther it can be felt from the magnet. The surface area of the magnet is the physical area of contact that a magnet can make with metal or another magnet. But how does this affect how far away it can extend into the environment? A magnet with less field strength is another, but which has a larger surface area, will be able to hold more weight than the smaller one due to the fact that there is a much greater area of contact over which the field can act. However, because its field strength is lower, it may or may not extend out as far into the environment as that of the smaller, stronger magnet. So the lodestones in these ancient accounts may have been large enough to hold a large amount of ferromagnetic material if in direct contact with them. But would their fields have been strong enough to levitate iron statues across a significant gap? It is possible, but will have to have been considerably large. Size does have an effect on how far away a field can act. The inverse square law, for instance, uses geometry to illustrate that field intensity is inversely proportional to the square of the distance from the source. And so it follows that the larger the source, the farther away it can be felt for a given field strength. We can see this with stars, as light also obeys the inverse laws. And we know that the larger a star is, the further away it can be seen. The document here attempts to give us a very good idea of just how strong the temple magnet was, by saying that the Konark magnet was so strong that it interfered with the sailors' compasses. Being able to have such a long-range effect on sailors' compasses from land seems unusually strong for a natural magnet like lodestone. But then again, it was said to have weighed 52 tons. Now, curiously, this compass interference sounds very similar to the accounts of pilots and sailors passing over and through the Bermuda Triangle. Does this suggest that there are enormous deposits of lodestone and other magnetite under Bermuda? And if so, is its placement the result of natural or artificial forces? And if artificial, then can the strange events occurring within the Bermuda Triangle offer any insight into a possible ancient magnetic technology? There's also evidence of an extinct ancient river close to the Konark Temple, which has recently been found via satellite imagery. So in this case, Any sailors traveling on this adjacent river might have noticed an effect of the magnet on their compasses. They may have noticed the interference. However, unlike in the Bermuda Triangle, it is unlikely that they would have been led too far astray, as they would have been traveling on a river which has a directionalized flow. The river itself is believed to have flowed into the Chandrabhaga Lake. But what is lodestone and how is it formed? Lodestone is a type of magnetite, all of which exhibits magnetism, but only lodestones display the distinctive north-south polarity, which we normally associate with magnets. Dr. Peter Wasilinski at NASA's Goddard Space Flight Center recently found that lodestones are produced from magnetite with a unique crystalline structure and composition, which gives them an increased susceptibility to magnetism. However, like ferrous metals, they still have to be exposed to a strong magnetic field in order to become magnets. It has long been believed that lightning, with its momentary but super intense currents, were the source of the magnetic fields, which turned this special magnetite into lodestone, as the Earth's magnetic field is deemed to be too weak. Now, it has been suggested that the Earth's magnetic field was much stronger in the distant past, but how long ago and how much stronger is still up for debate. Dr. Wasilinski, however, has recently demonstrated the ability of lightning to magnetize pieces of magnetite at a New Mexico laboratory specializing in lightning studies. And so we might wonder if the ancients also noticed this and devised a method to create strong magnets artificially by harnessing and attracting lightning. It is feasible that this could have been done by suspending the ends of a long metal wire into the air before an impending lightning storm and placing the other ends near or around pieces of magnetite or even iron. By doing this, perhaps even stronger ancient magnets, custom made to any size, could have been produced. The second season, third episode of the show, Ancient Discoveries, which aired on the History Channel in 2005 and entitled Machines 2, explained that the ancient Greeks and Romans indeed knew how to attract and harness lightning, but claims that it was used mainly as another part of the ceremonies to demonstrate the power of the gods, as well as to produce much needed rain, as rain often follows a lightning discharge. If the ancients did understand the connection between lightning and the magnetism of lodestones, then it certainly stands to reason that they could have used these same principles along with other methods in order to create artificial magnets or to even strengthen natural ones. And speaking of large magnets, just how large would the Konark lodestone have been? Magnetite has a density of about 322.8 pounds per cubic foot. So the 52-ton or 104,000 pound lodestone at Konark would have had a volume of about 322.2 cubic feet. And so possible dimensions of the Konark magnet in units of feet could have been 10 by 10 by 3.2, or 8 by 4 by 10, 7 by 5 by 9.2, 4 by 4 by 20, or even other combinations. To give an idea of scale, the latter product has a length dimension of 20 feet, which would be as long as a mini school bus. So as we can see, it was a truly massive magnet. So perhaps we can assume that it was not only strong enough to affect the compasses of travelers on the nearby river, but also strong enough to attract a large piece of iron over a significant gap. But would full levitation of a formed piece of iron have really been possible even with diamagnetic materials? Here we see a diamagnetic experiment in which a small cube is in stabilized levitation. But in this experiment, as in most diamagnetic levitation experiments, the levitated body is a permanent magnet. But the iron statues in these accounts will only be temporary magnets when placed near or within strong magnetic fields. And as such, it is likely that their temporary magnetic fields will have varied depending on how close to or how far they would move from the magnets when the system was being calibrated by the builders. And so the big question is, can iron or other metals, especially of non-uniform shapes like iron statues, levitate in the same manner as the uniform permanent magnets in the diamagnetic experiment here? The accounts certainly seem to make that claim. The aforementioned ancient image in the temple at Alexandria probably being the most well-known. On a third season episode of the program Ancient Discoveries, called Machines of the Gods, or Machines 3, a life-size iron chariot was said to have existed within the temple of Serapeum of Alexandria, which was commissioned by Ptolemy III. According to the program, Serapis was the equivalent of Apollo the sun god, while other sources relate Serapis to Zeus. The iron chariot was said to have been part of a religious ceremony in which it would be slowly drawn towards a giant statue of Serapis, and at the height of the ceremony, which coincided with the light of the sun striking the statue's lips, the chariot would levitate and float just in front of the deity's face, presumably by the enormous magnet embedded within the ceiling above. It's an incredible story. But again, could iron statues, especially due to their non-uniform shapes, be able to levitate in the same way as permanent magnets in the solid geometrical shapes, such as discs, spheres, and cubes? Additionally, going back to the diamagnetic experiment here, we can see the very close tolerances that are needed to reach stable levitation. In fact, though the kit's instructions recommended a stack of 5 pennies on either side as pillars, I didn't achieve stable levitation until I removed 1 penny from each side. Scaling this experiment up would likely result in similar close tolerances. Not only would this make the effect a little harder to see from the ground, but the resulting tight spaces means the statues will have to be nearly as tall as the space between the ceiling and the ground. When we think of religious temples, especially ancient ones, one feature we may notice is the sheer spaciousness. They usually have very tall ceilings and large spaces in between the walls, sometimes with intervening pillars to hold up the large roofs. The sheer vastness of the ceremonial spaces can amplify certain low-frequency sounds. Such sounds have the tendency to inspire fear and unease, like the low growl of large dogs or the low rumble of thunder. Additionally, the large spaces help to make the patrons feel existentially insignificant and very small in comparison. This combination would serve to invoke the sense of being in the presence of vast supernatural powers, the powers of the gods. And so it seems to me that the close tolerances required for diamagnetic levitation might serve to undermine this quality of spaciousness. Attempting to levitate a piece of metal seems even more of a challenge. We see here that I am attempting to levitate a short metal bolt in the same way as the magnet. The bolt does stand up and will even attract to the lifting magnet, but it does not stably levitate between the two bismuth slabs. Then I thought of placing a small magnet on top of the bolt, as I figured that the ancients might have placed a magnet within the statue's head in order to increase the magnetic interaction with a large lifting magnet. I also tried putting in an identical magnet at the bottom, but to no obvious avail. With diamagnetism, the closer the magnet moves to the diamagnetic material, the stronger the diamagnetic repulsion as the circulating currents within the material get stronger. But in a piece of metal, the field within it may be too variable, depending on how far it is from the magnetizing field of the lifting magnet. In the illustration here, the metal gets farther from the magnetic field, and thus its temporary magnetism is likely weaker. So the bottom part probably doesn't have enough magnetism to induce a proportional diamagnetic field from the bottom bismuth slab, whereas a permanent magnetic field will retain its strength regardless of how far it is beneath the lifting magnet. And so, if it moves closer to the bottom bismuth slab, it is repelled upwards, and if it is repelled too high, then the top slab will repel it from the top. Eventually, with enough coaxing, the magnet will levitate in a fixed position in the center of the gap, where the forces level out to zero. When the magnet is bumped off center, the repulsive forces tend to push it back into equilibrium. But this will become more complicated with a piece of metal or iron. Perhaps the statues were permanently magnetized by vibrating them via striking or even heating while placed within a magnetic field. This would have allowed them to retain their magnetism and become permanent magnets, though this process was not mentioned in any of the accounts. Another possible way that the ancients could have achieved stable levitation, other than, or perhaps in addition to diamagnetism, would be to employ time-varying magnetic fields. Such fields can be varied in strength so as to pull on a magnetized object and then cease pulling on it when it gets too close to the lifting magnet. Or it could be even reverse its polarity and push the magnetized object away if need be. This is how floating, hanging globes work. The actual technique is called attractive electromagnetic suspension, or EMS, and works by employing sensors and feedback loops to constantly alter the current being sent to the electromagnets, allowing their magnetic field strengths to vary as needed. This allows the system to cancel the inherent vertical instability. As mentioned before, an advantage with attractive suspension maglev is that it has inherent lateral stability. As a suspended metal or magnet is attracted to the lifting magnet, the natural tendency is for the object to be attracted upwards, a tendency which typically overwhelms any side-to-side movement. As such, it is only the vertical instability which needs to be countered by varying the strength of the lift magnet to lift and stop lifting alternately. But can a time-varying magnetic field be generated without modern electronics? The answer is a resounding yes. One way is shown here on the YouTube channel, The Action Lab. On one of the videos entitled Magnetic Locking Without a Superconductor, we can see not only the levitation of a small magnet, but a magnetic locking technique that is practically identical to quantum locking of a superconductor. Normally, a superconductor repels all magnetic flux lines, but tiny imperfections in the superconductor can allow some of the magnetic forces through. These magnetic channels are called flux tubes. These tubes cause the magnetic field to become locked in all three spatial dimensions. But the technique demonstrated here is called polarity-free magnetic repulsion, a technique invented by an engineer by the name of Hamdi Ukar. The basic idea starts with the premise that when like poles of a magnet are brought together, they will tend to flip around so that as to align their poles in the same direction, this configuration being the most stable energetic state. But magnets, like any physical objects, have both mass and moments of inertia. the moments of inertia being directly proportional to the magnet's mass and dimensional lengths. And as such, it takes a certain finite amount of time for the magnets to orient themselves. So if one of the magnets can be rotated fast enough with a Dremel or another high-speed rotational device to stay ahead of the magnet's reorienting attempts, then the floater magnet will be lifted and held in place, being alternately attracted and repelled as it attempts to catch up with the spinning magnet. As it lags behind, out of phase with the spinning magnet, it becomes magnetically bound or locked in space. The YouTuber was inspired to experiment with the unique attempt or technique after reading the paper by Hamdi Ukar. There is a link to both the Action Lab video and the paper by Ukar in the description below. Although it would not work in the current application which we are studying due to the fact that the magnet has to be spinning, it is nevertheless an amazing discovery and proves that purely mechanical ways can be devised to stably levitate magnets without superconductivity, modern electronics, or even a feedback system. A second way is shown here in a video by another YouTuber. It is essentially a variation of the diamagnetic levitation technique. Again, it involves a magnet or a magnet stack placed in between upper and lower plates of a given material. In this case, plates made of thick copper rather than bismuth, and a lift magnet situated above the entire assembly. However, in contrast to the diamagnetic experiment, which employs continuous atomic microcurrents, the floater magnet stack will not levitate indefinitely when the lift magnet is in a static position, as the induced macro eddy currents only manifest when the floater magnet is in motion, and hence generating a time-varying magnetic field. And so likewise, the magnetic field of the lift magnet must be time-varying and able to increase and decrease in the space above the floater. This is done by manually adjusting its position. Subtle movements of the lifter magnet have to be made continuously in order for the eddy currents to manifest. Moving the lift magnet in this up and down manner results in the levitation of the floater magnet stack with surprising stability. These eddy currents, again, while not granting indefinite stability, do offer a semi-stability by granting a type of electromagnetic braking effect. So as the floater magnet falls, this downward motion is significantly impeded by the eddy currents generated as it approaches the bottom plate, which results in a repulsive force from that plate. Simultaneously, eddy currents are generated in the top plate as it moves away from it, resulting in an attractive force towards that plate. This follows as the currents generate a magnetic field which opposes the field of the moving magnet stack, thus slowing its descent. Moving a magnet increasingly close to a piece of non-ferrous metal generates an opposing magnetic field which counteracts that approach. And a magnet moving increasingly farther away generates a field which counteracts its abduction. We've seen this same force field-like effect in demonstrations of dropping a strong neodymium magnet into a non-ferrous copper or aluminum plate, or dropping a magnet through an aluminum or copper pipe conduit as shown. It is an effect that we've seen numerous times, yet it never ceases to amaze. When the floater magnet stack is pulled up towards the top plate, the opposite effect happens with an attractive force induced in the bottom plate and a repulsive force in the top plate, thus slowing and counteracting its ascent. One thing we may notice here is the significantly relaxed spatial tolerances between the floater magnet stack and the plates as compared to the diamagnetic version, with the magnets not having to be so close to the plates to float stably. This would allow the architecture of the temple to maintain a greater degree of spaciousness, which, as previously mentioned, can bring in a very important visceral element to the feeling or sense of otherworldliness. I attempted to duplicate this experiment using magnets and two 1/2 inch thick aluminum plates. We can certainly see the electromagnetic cushioning effect at work, but the slower, more controlled levitation remained elusive. I was eventually able to get full flotation of the magnet stack by significantly reducing the open space, but this makes the levitation less obvious from a distance. Going back to the YouTube video for analysis, we can see that they were able to maintain very good spacing between the magnets and the plates. We can see that the copper plates are much thicker than the 1/2 inch thick aluminum plates that I'm using in my experiment. We can also see that the stacked magnets seem similar in size to those that I'm using. And in that case, the height of the stack should be around 3/4 of an inch. Hence, I estimate the thickness of the copper plates at between at least 1 and 1/2 inches thick. This is significant because not only do thicker plates make better conductors of electricity and hence eddy currents, but copper itself is a better conductor of electricity than aluminum by about 40%. Testing this theory with a purchase of 1-inch thick copper blocks, we can see that this is indeed the case. The copper's greater thickness and improved conductivity results in stronger eddy currents and hence greater braking. This slows the normally much quicker movements of the magnets when they interact with each other, allowing the magnet stacks positioned to be varied manually. The greater eddy current conduction of the plates also gives us some further insight into how superconductors work as materials with near zero resistances, which result in massive eddy currents and countermagnetic fields when in the presence of strong magnets. Going back to the document here, it seems to support the eddy current maglev theory over the diamagnetic method alone. It says that copper plates were placed beneath the idols so that the magnetic fields will resonate in the surroundings. And so here, we appear to get confirmation of both the copper plates as well as time-varying magnetic fields, as only dynamic fields can experience resonance. But again, with the metal plate method, the floater magnet will float up and then back down, slowly enough to amaze, but it will not remain in a fixed position as with the diamagnetic version. As the lift magnet is brought downward closer to the top metal plate, the magnet stack floats upward due to magnetic attraction. The eddy current slows this movement, but if the lifter magnet remains in that lower position, the floater stack will almost always contact the underside of the top plate and remain there due to its attraction to the lift magnet through the top plate. This can be prevented by raising the lift magnet just enough to reduce the attraction. Gravity then ultimately regains control and the stack begins to fall, this motion again being slowed by the electromagnetic braking. The lift magnet would then have to be lowered again in order to counter the complete descent of the floater stack. These actions have to be repeated constantly for the stack to remain in midair. If this could be done at just the right frequency and duty cycle, then we can see how stable levitation could be achieved. This could be achieved manually, as shown. It could also be achieved electronically or even mechanically. An electronic version will operate nearly identical to the EMS system of floating globes, switching the lift magnet on and off at a given rate. The main difference is that the normal EMS setup requires much faster variations on the order of about 100,000 per second, which must be realized electronically. A non-electronic mechanical version using thick conductive plates could operate via much slower impulses due to the eddy current braking. It could hypothetically be made by attaching the lift magnet to some type of elastic or compressible material, which could be pulled or pressed in order to set it into harmonic motion. It could be kept in motion by applying a continuous input of energy, perhaps by flowing water or some other mechanized device, which we know that the ancients knew how to create, or regular energetic input by a human operator could manually keep it in motion. In the animation here, the lift magnet cycles closer to and farther from the top metal plate, and hence also the sandwich magnet stack. It is basically the same as the EMS system used in the previously mentioned floating globes, only the needed frequency has been greatly slowed down because of the eddy current braking properties generated by the non-ferrous plates. As the lift magnet moves closer to the floater magnet, the latter is pulled up, but its ascent is slowed by the braking. By the time it begins to move, the lifter magnet moves farther away. The floater magnet then begins to fall, but again slowly due to electromagnetic braking. At just the right frequency and duty cycle, the lift magnet should alternately pull on the floater more and then less in a repeating pattern. As shown in the clip, I attempted to test this idea with a mechanical oscillator to keep it kept in constant motion. It is kept in motion with electronics, but this is just to prove the viability of the concept. In ancient time, this most likely would have been achieved by purely mechanical means. The varying strength of the lifter's magnetic field in the space above the floater causes the floater to vibrate at the same rate, minus some eddy current drag, causing it to be in constant motion. The eddy currents generated by the moving floater causes it to levitate. As it does, the frequency and duty cycle of the oscillating lifter would need to be altered to prevent it from coming into direct contact with the top plate as shown. It would be difficult to achieve this with only a mechanical harmonic system, however. An alternative would be to find the equilibrium point through observation with the hand until the magnet stack feels like it would be stable and then release it. This is how a modern floating globe is placed in position. The globe does not levitate from the bottom surface. Rather, the operator places it into its equilibrium position. This experimental setup, though not perfected, demonstrates potential as a stable levitation system, as we can see that the floater's ascent is notably slowed. This would suggest that if the frequency and duty cycle were just right, then the magnet stack would stably hover, even if it's vibrated somewhat due to the oscillating lift magnet. I got the best results at about 2 cycles per second and a duty cycle of about 23%. For a large magnetic statue, though, it would have to be placed on a spacer block while the oscillating magnet's frequency and duty cycle were adjusted. When the operator sensed that the full weight of the statue is being magnetically supported, they would then remove the spacer block to reveal the statue floating in place. It would be a delicate operation and quite tricky if the temple lifter magnet were indeed megalithic in size and weight, as described in the account of the temple at Karnak. We can imagine how oscillating a 52-ton magnet up and down in the ceiling would be problematic, to say the least. And speaking of oscillation and vibration, we may also recall John Worrell Keely's claim that the proper acoustic vibrations could intensify magnetism and likely mitigate it as well. This would eliminate the need to physically oscillate the actual lodestone magnet. Instead, the lodestone's magnetic field would be enhanced and mitigated, presumably at the atomic level, due to acoustic manipulation of the magnetic material itself. Interestingly, Mesmer, like Keely, also suggested that magnetism could be augmented by sound. This has yet to be demonstrated, but if viable, then it would be yet another way to generate time-varying magnetic fields to produce stable levitation. But could this proposed acoustically induced magnetism also help to solve the mystery as to how the ancients could have been able to create powerful magnets or enhance natural magnets to be strong enough to achieve these feats? Or did they simply create more powerful magnets using the hot cold or striking method as previously mentioned? It might also be feasible that they added certain impurities to molten iron in order to create much stronger magnetic alloys, just as we do today. The Ancient Discoveries program also mentioned another temple miracle involving seated statues of Venus and Mars. The figures would be slowly brought together, after which point they would leap into each other's arms in a passionate embrace. This was said to be possible because one statue was said to be made of iron, while the other of magnetic material, probably lodestone. And if so, then this certainly demonstrates that the ancient engineers had access to powerful magnetic forces. The ancients were also practically familiar with feedback loops. Hence, it is quite possible that a magnetic levitation system, similar to the metal plate version, could have been combined with a mechanical feedback loop. The Greco-Egyptian inventor and mathematician Hero or Heron of Alexandria invented a float valve which could sense the level of wine in a bowl and refill it after guests had ladled out wine. And Greek engineer Philo of Byzantium discovered or developed a self-regulated oil lamp. Both are examples of 2,000 plus year old negative feedback systems, hence proving that the ancients also had discovered the principles of feedback and self-regulation and knew how to develop mechanisms based on these principles. A feedback system based around the metal plate levitation version is shown in the animated diagram. It would involve an initial input of energy into the system by lightly pushing the floater upward to set it into motion. A sensing device, probably a magnet, itself attached to a lever, would change its position as the floater magnet rises up from it. The lever would exert a force on a string attached to the end of another lever, which houses the lift magnet on the opposite end. This would raise the lift magnet after the floater passed a certain point. The idea is that the floater would begin to slowly fall back down due to the decreased attraction as the lift magnet moves further away. As it falls, the tension in the first lever would be released, and the lift magnet would descend back down to its original position to restart the process. Energy would likely have to be inputted into the system at regular intervals, but it would be a self-regulated system. I am working on a model to demonstrate this, and I will make a follow-up video if successful. And as for the metal plates themselves, we see that they had to have a thickness in the neighborhood of 1 inch to achieve a decent floating effect of even 1 inch diameter magnets. And if using diamagnetic material, they also have to be quite thick just to levitate a much smaller cube magnet. And so we may wonder just how thick the plates of either material will have to have been in order to float a heavy iron statue. Assuming that ancient engineers were able to do this, it seems that the magnitude of the diamagnetic or eddy currents will have to have been enormous and will have to greatly increase in relation to the weight of the statue itself. And so the hidden diamagnetic or copper plates will have to have been absolutely massive, even megalithic in size themselves, in order to conduct such currents. It may have been necessary to insulate any metals in the immediate area, but of course, the patrons likely would not have been allowed to come too close anyway, and the plates would have been cleverly concealed within the architecture as well. If such a method was used, then it would be difficult to imagine that the ancients could effectively employ eddy currents in levitation and not know anything about electricity, as is often claimed by mainstream academia. Perhaps we could surmise that the statue was hollow in order to reduce its weight. It is reasonable to assume that this would reduce the magnetic force required to lift and suspend it. However, the hollow region within the statue would significantly lower the magnetic permeability, thus reducing the overall magnetic force. The magnetic lines of force already have to cross over significant gaps between the upper and lower parts of the statue in order to achieve the levitation effect. Seeing the arrangement as a large magnetic circuit, we can see that air, with its very low magnetic permeability, will introduce significant resistances into the circuit. So if a hollow statue was the answer, then a delicate balance will have to be found between the lower weight of the hollow statue and the weaker magnetic conduction exhibited by the hollow region within. A more practical solution might be to conceal strong magnets within the statue's head and feet. This would allow the statue to be hollow for the reduced weight advantage, but without the setback, as the reduced magnetic permeability will be compensated for by the magnets on or within the head and feet. Another interesting detail in the metal plate version is that the 3-inch diameter ring magnet seemed to enable a noticeably larger degree of control over the floater magnet stack than the 1-inch diameter magnets did, enabling the stack to float perfectly in between the plates with fewer adjustments. I believe this may be because the magnet's larger size gives its field a much larger working area, and larger working cross-sectional areas tend to enhance stability and overall strength in most mechanical and energetic systems. Perhaps this is another reason why the lodestone described in the Sun Temple at Konark had to be so incredibly large. This would likely hold true then for the other levitation accounts as well. Now, if the continuous levitation was too difficult to maintain, even with such skilled construction, this wouldn't necessarily mitigate the spectacle. The momentary controlled flotation of a large object would still be an incredible feat, perhaps even more so. Thus, it wouldn't be necessary for the statue to float indefinitely. Ultimately, the operators really just want some increased degree of control over the movements of the magnetized statue, such that it could be operated manually. And this is what electromagnetic or eddy current braking does. It slows down the response time needed to correct the magnetized object's motion so that it doesn't just slam up against the lifting magnet when it is moved closer to the top plate. And likewise, it slows the object's descent so that it doesn't smash into the ground when the lifting magnet is moved farther away. The slamming attraction is what we've all seen and experienced when normally handling magnets. Eddy currents quite literally puts the brakes on this, which results in a type of slow motion effect. Instead of being made to float indefinitely, the statue could be made to levitate in a brief arc or series of arcs during the dramatic height of the ceremony. Perhaps this would be made to coincide with a beam of light from the sun channeled into the worship space. Adding in artificial thunder could provide even more gravitas, something which the ancient Discoveries program explained was actually a regular part of ceremonies. After its astonishing flight, the statue could just be settled back down into the temple floor. This method, or one similar, would have to have been needed for the flying chariot at Alexandria rather than diamagnetism, as the chariot didn't just float a few inches above the ground and below the ceiling. Rather, it is said to have risen from the floor and to hover just below the ceiling and in front of the face of the giant Serapis statue, a statue which, according to the document, or this document here, was over 13 feet tall. In the ancient Discoveries program, however, the height of the statue appears to be much, much greater. The document also mentions the height of the temple itself, which is given as 256 feet. So it seems possible that an even larger statue may have inhabited the sanctuary. Either way, the chariot would have been lifted to a significant height, in stark contrast to the close tolerances mentioned in the other ancient levitation accounts. This is believed to have also been made possible by a large magnet embedded within the ceiling. Even still, it couldn't simply be a matter of pulling an iron chariot under a large magnet and having it levitate gradually in a controlled manner, and then hover in place under the static magnetic field of a large magnet. As we've experienced and observed, magnetism really doesn't work that way. These clips show what would in fact happen if a metallic or magnetic object is brought under a large powerful magnet. The same thing would happen if an iron statue or chariot were brought within a magnetic field that is strong enough to lift it. The forces between magnets and ferrous materials do not change in a directly linear manner, but can vary according to the square and in some cases even the cube of the distance from one magnet's poles to another magnet's poles, and between magnets and ferrous materials. This results in dramatic differences in magnetic energy and force from one point to another. And as we know from Newton's second law, force equals mass times acceleration. So the greater the force, the greater the acceleration, resulting in these materials typically smashing together when they do come into contact with each other. So if the field of the embedded ceiling magnet could manage to exert a substantial lifting force on the iron statue that far below it, then rather than a controlled flotation, the statue would instead be pulled upwards, increasing in speed and acceleration over a considerable distance until it smashed into the magnet, and will likely do so with enough force to seriously damage both itself and the magnet. And so at the very least, there will have to be some kind of braking of the statue's ascent, possibly using eddy currents as previously demonstrated. And likely there will also be need to be a way to regulate the field using manual control or a mechanized negative feedback system, as also discussed. If operated manually, then a strong leverage system will have to be developed in order to enable a person to easily alter the position of the heavy lifter magnet in a very precise manner, raising it and lowering it in order to raise and lower the chariot, especially since the lifter magnet will be attracting the statue and magnetically carrying its weight as well. The entire arrangement could easily weigh close to 1,000 pounds or much, much more. But at least for the static levitation, perhaps the intrinsic stability benefits of diamagnetism can be combined with the relaxed tolerances of the metal plate system. This might take the form of thick slabs of diamagnetic material being used in conjunction with non-ferrous material. We can see in this demonstration that a piece of non-ferrous metal moved closely to the magnet stack from the sides results in a slight pushing force. Likewise, holding the plate close to the stack and then pulling it rapidly away results in the stack being pulled, as the generated fields generate an attractive force opposing the direction of the plate to counteract this movement. The faster the movement of the plate, the greater the force, as the magnitude of the induced currents are proportional to the rate of change of the magnetic field in a given region. Hence, we might imagine the side posts as well as the top and base of the giant levitator as being composed of layers of non-ferrous metal on the outside and thick layers of diamagnetic material, which would line the inside. Theoretically, in this arrangement, any movement of the large magnetized statue would be greatly slowed by the metallic plates. This might allow the comparatively weaker forces of the inner diamagnetic materials the ability to slightly push on the statue and keep it in equilibrium. As previously mentioned in the document on the Temple of Konark here, the arrangement of these magnetic materials would depend on the nature of the levitational system itself. As we already know, there are two main types of conventional non-superconductive suspension systems, the attractive and the repulsive. For either system to work, the main lift system has to have an overall equilibrium, which is provided by either a perfect time varying mechanism or a negative feedback system, whether electronic or mechanical. However, each system can still suffer instabilities. For instance, in a repulsive suspension system, as shown here, a magnet platform is positioned underneath another magnet to levitate the latter and any load that it carries via magnetic repulsion. It is normally stable due to the self-correcting electronic feedback system within the platform. However, since it is a repulsive suspension system, it is still vulnerable to horizontal instability despite its feedback system. These instabilities can throw the system out of balance and overwhelm the levitational effect. The severity of these instabilities depends on the length and irregularity of the suspended object. This introduces a moment of inertia or tendency to rotate and fall. But this instability can be effectively countered by an attractive force between magnets embedded within the beam above the arrangement and magnets embedded in the top of the object itself, as shown here. A better example is shown in the demonstration here, where we can see that the statue's length and moment of inertia make it pretty much impossible to balance and stand on its own atop the levitator. But by placing magnets above the statue, oriented to attract magnets that are placed on it, we can get perfect stabilization. For the attractive suspension system, the magnetic feedback platform is positioned above the magnet rather than below it in order to levitate it and its load via magnetic attraction. Again, it will have to already be stable via a perfectly timed or negative feedback system. But being an attractive suspension system, it is still inherently vulnerable to vertical instability. This instability could result from external forces, which could introduce unwanted vertical oscillations or displacement within the system, causing the suspended load to oscillate up and down or displace out of equilibrium. If great enough, the oscillations or displacement can throw the entire system out of balance and cause the levitation state to be lost. In contrast to the propulsion system, we might theorize that magnetic attraction forces operating in the horizontal plane rather than the vertical could serve to counteract this instability. This could be accomplished by embedding magnets in ferromagnetic materials within the side posts on either side of the suspended object, which would attract magnets embedded within the sides of the object. This should serve to dampen and mitigate any vertical forces which could cause runaway oscillation or displacement. As we can see here, the floating globe has a magnet on either side of its equator, which are oriented to attract to magnets on the inside of the posts. Without the posts, touching the top of the globe with a paperclip disrupts the magnetic field, causing the globe to fall. Shaking the platform up and down also causes oscillations with the same result after about 3 shakes. But when the posts are up, with the stabilizing attractive fields, I can touch the globe with a paperclip without destabilizing it so easily. I can also shake it about twice as many times before it destabilizes. These stabilizing forces would likely improve with the increasing size of the magnets. The ancients, also being so distinctly aware of natural earth energies, might have used additional materials to guide, shape, and integrate natural geomagnetic fields into the artificial temple system using a variety of materials and metals. This could have theoretically resulted in additional magnetic energy flowing into the magnetic circuit for even greater lift force and control, and perhaps more relaxed gap tolerances. Any such levitation system would be a very delicate process, as we can see even with small models. But it's certainly no question that the ancients could work with astonishing precision and close spatial tolerances, even on a megalithic, multi-ton scale. And precision of spatial tolerances is one of the main deciding factors in the efficacy of any maglev system. And speaking of tolerances, we can see here that larger levitation gaps are preferable, as it would result in a more startling spectacle. But is there any way to quantify how high above the ground and below the ceiling these ancient statues could have floated? A couple of modern-day accounts might offer a hint. One account involves a 16th century temple in India known as the Lapakshi Temple. The famed temple has 70 stone pillars, one of the pillars which appears to be floating from the ground and has been dubbed the hanging pillar. The space in between the pillar and the ground is not large, but it is noticeable, and it is possible to pass a sheet of paper or clothing between the bottom of the pillar and the ground. It was once believed by some to be a levitating pillar, defying gravity and floating in mid-air, a wonder which drew many tourists each year. However, the pillar does not float via any gravity-defying principle, but rather is simply hanging from the ceiling. There are slightly different accounts on how the pillar came to be this way, but the common detail seems to involve a British engineer who worked on repairs of the temple during the pre-independence era of India. It is said that he noticed that it was not touching the ground and wanted to know how it was being supported, most likely so that he could repair it. However, he found that it was practically impossible to remove and only managed to dislodge it to a slight angle. This has resulted in it now being only partially hanging, with one of the corners resting on the temple floor. Another account involves a temple in Bhutan, a small country situated in the eastern Himalayas between Tibet and India. At this temple, there is said to be a mysterious floating statue of Dorje Phamo. One leg of the statue is crossed at the knees, and the other is standing, but does not touch the ground. Similar to the hanging pillar at the Lapakshi Temple, people can test this disconnection from the ground by passing paper money below the statue's feet from one side to the other. It says here that as you visit the temple, the caretaker will tell you two things about the statue. First is that the statue is literally floating in the air. He will take you to the altar and enclose the statue. He will make you believe that the statue is standing in the air by sliding a money note below the foot of the statue. Witnessing that moment will amaze you. You will also be able to see a small gap between the statue and the base. And so the gap between the statue and the ground, just as with the hanging pillar, must measure only in fractions of an inch. I am unable to find any specific information as to the size of the statue or its physical composition. But as with other ancient Tibetan statues, it is likely life-size and made of a core of wood or other organic material with an outer layer of metal, most likely bronze. And if it is made of bronze, which is a non-ferrous metal, then it is unlikely that it is a magnetically levitated statue of the same kind as in the previous discussed accounts, unless of course it has magnets hidden on the inside. Perhaps its true means of support is simply hidden from view, as with the hanging pillar. Either way, these accounts both suggest that, though more relaxed tolerances are more visually impressive, large objects would not have to float very high in order to be noticeable and impressive. Likely just seeing something so large and heavy with no visible means of support will have the power to enchant, despite the tight spatial tolerances. Ultimately, the Ancient Discoveries episode suggested that it was more likely that a complex network of wires was used to actuate the flying chariot of Alexandria. I might have to agree that a complex wire system is likely safer and more feasible. A combination of low lighting to conceal the wires and dramatic theatrics could trick the untrained eye and mind into believing that the contraption was floating freely in midair. However, the account seems to almost insist on the use of magnetism. Is it possible that a large-scale pseudo-levitation system was used instead of a purely wire or purely magnetic levitation system? After realizing the challenges of full levitation, the ancients might have devised a more practical solution, which involved anchoring the bottom of the statue to the temple floor by a strong cable or even a chain. The head, and perhaps a strong magnet concealed within it, would then be able to float just out of reach of the massive ceiling magnet via magnetic attraction. The large lodestone magnet could have been made to move back and forth and side to side, moving the suspended statue along with it, which would add to the illusion of free floating like a helium balloon. The cable or chain could have been coated with a substance to make it sparkle in the sunlight, giving the idea of it being imbued with magical or divine binding power, preventing the being from ascending. A possible accompanying narrative could be that the god or saint is attempting to ascend to the heavens, but is supernaturally shackled to the ground, trapped between heaven and earth, perhaps reflecting our own human dilemma of ever aspiring to the spiritual, but often tempted and bound by our baser instincts and desires. As we can see, narrative and context are often vital parts of most magic. Of course, this is not to say that full magnetic levitation was not achieved by the methods demonstrated on a small scale, or perhaps some variation of them. As mentioned before, I would put little past the ingenuity of the ancients. Whatever method that they used to float the statues, whether by wires, pseudo-levitation, or full magnetic levitation, it undoubtedly would have been truly spectacular for the patrons and empowering and enriching for the temple priests. And so, if we're talking about cultural memories and archetypes, then they would most likely have resulted from a conglomeration or melting point of different ideas and phenomena, including magnetically levitated statues, perhaps even the acoustic lubrication and levitation of stones. These, in addition to the incredible flying ability of birds and their enduring idea of divinity as a state of being that has inherent buoyancy, free from the normal constraints and limitations of humanity. Perhaps the concept of large floating statues in particular has been preserved and re-envisioned in modern times in the forms of mysterious monoliths which hover over the Earth's surface, as can be seen in the movies like Epoch, Arrival, and various sci-fi TV shows, though still representing the same sense of otherworldliness as the floating religious artifacts. The basic concept also seems to be preserved in visuals of levitating vehicles and conveyances present in many futuristic media. In modern times, levitation, while still regarded as somewhat otherworldly, is often seen less as an element of the spiritual and more as an element of either alien or advanced human technology. The ancient accounts do prove one thing for certain, however, and that is that the ancients were at the very least thinking in the direction of large-scale levitation well over 2,000 years ago, and likely much, much earlier. And it is also likely that they would have tested the idea first on small-scale models. They would then have identified the technical challenges of such attempted arrangements and either abandoned the idea altogether or found a way to overcome these difficulties. Some may even still question whether or not such magnetic levitation could even work on anything larger than small models. This uncertainty may reflect Eric Laithwaite's claim that permanent magnet systems become more inefficient with increasing scale, while electromagnetic systems become more efficient with increasing scale. There is solidarity with Laithwaite's assertions expressed in the document here, which says that generally, the volume of space needed to produce a given static field will be less for permanent magnets when their working gap is small, but electromagnets win in larger devices. However, it also says that this decrease in efficiency itself decreases whenever higher energy permanent magnetic materials are developed. In definitive proof that permanent magnets can levitate life-size structures and masses is seen in this futuristic magnetic hover bed, which is currently on the market. Though it requires 4 thin wires for lateral stabilization, it is nevertheless a dazzling visual, levitating above the floor at what appears to be at least 2 feet in height, and boasting a holding capacity at just over 1,500 pounds. I have no doubt that free-floating versions with no need for external stabilization will be available soon. Levitation has always invoked a powerful sense of awe and of the extraordinary, even though those are occasions when we know that it's just an illusion, as in a magician's act, or a clever optical trick. Witnessing even a small object being lifted into the air in a controlled manner by an invisible force can be both spooky and unsettling, as well as exciting and mystifying. It also has unmatched potential for lifting and transporting over more conventional means, which are more subject to energetic losses caused by friction. Hence, it is very conceivable that the ancients would have attempted to figure out how to achieve levitation by various means for use in art, mystery, and perhaps even construction. There will be much more to follow on this subject. Until then, thanks for watching, and as always, stay tuned.